I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss a few numericals based on diffraction grating. So before we go into the numericals, let us first understand the theory behind this topic, that is diffraction grating. So what is diffraction? So diffraction is nothing but the bending of light around the corners of obstacles when the size of the obstacle is comparable with the wavelength of light. Means the light will not bend at any obstacle, but only when the size is comparable with the wavelength of light. So in the figure here, what we see is an obstacle. This is an object. So this is the obstacle. Light is incident like this. Now when light is incident on this obstacle, according to Huygens principle, each point will act as a secondary source. So these points which we are seeing, they will act as secondary sources and start sending secondary wavelengths. So what you see here is, naturally, if we are talking about light bends around the corners of an obstacle, if it bends, we should get only a shadow here, and there should not be anything seen in the geometrical shadow here. But what we are observing here on the screen, if you see, this is the screen that is placed at a distance d, you see that it extends into the geometrical shadow. What happens here is, all the waves, the secondary source is sending out wavelets. These waves, when they interfere with each other, one thing is diffraction, the bending is happening, and depending upon the bending and the waves that interfere with each other, you get a diffraction pattern. So what you get in a diffraction pattern here is, you will have a central maxima which is very bright. This is the central maxima. And then you have secondary maxima on either side of the central maxima. So this is one more maxima and the other maxima. So you have a central maxima which is bright. Then there is a dark band, again a bright one. This I can say, if this is the central maxima, this is the secondary maxima. First secondary maxima, n is equal to 1, I can say. This is also a secondary maxima, n is equal to 2. So on either side you have n is equal to 1 and n is equal to 2. So what you are seeing here is a diffraction pattern. So whenever you have a slit, when light is incident on the slit, each point acts as a secondary source and sends out wavelets. These wavelets will interfere with each other, and because of that you are getting a diffraction pattern. So how we are getting an interference pattern, we have already discussed. When they are arriving in phase, there is constructive interference which gives rise to a bright band. Whenever they come out of phase, it gives rise to destructive interference which gives a dark band. Now, once we understand this phenomenon of diffraction, what is diffraction grating? Now, in theory, we have already discussed about diffraction due to single slit. If there is only one slit, means light passes or bends around the corners of one slit. Double slit also we have seen. Then we have seen n slits. Now, if this light is incident on n number of slits, there are many slits. The n can be as big as 15,000, or it can be more than that. So when the number of slits is more, then how diffraction takes place. That is what we are going to understand. So for that, first we will see what a diffraction grating is. So how do we get a diffraction grating? You take a plain glass plate like this, a transparent plain glass plate, and a large number of parallel slits of the same width, and they are separated by opaque spaces. That means 15,000 lines are drawn on 1 inch width of the grating. So what we are doing here is take a plain grating, a transparent one, and draw lines on this grating with the help of a diamond point. Why diamond point? Because for precise lines. Okay, and per inch, what we are doing here is, in this example we are talking about 15,000 lines per inch. So the ruled lines will become opaque to light, means through that light cannot pass. But the space between the two lines is transparent and that acts as a slit. So when we have drawn 15,000 lines, there are 15,000 lines which are opaque, which do not allow the light to pass. But the regions in between these 15,000 lines, they are opaque and through them light can pass. So that corresponds to n number of slits. So now how do you write the width? Because in all numericals we are going to refer the width of each slit as E plus D. So how are we going to understand that? E is the width of each slit and D is the separation between the width. So you see here, if you have, this is D, I'm writing this is E, and the separation we are talking as D. Now what is the width of each slit if you write is E plus D? We will call it as a grating element. So the width of the grating element is given by E plus D, or the slit width here is E plus D. So we'll be referring to this in all numericals. So you need to understand what is this E, what is this D. E is the width of the slit, means the region through which light can pass. That is the region between two lines that are drawn. So like that we have drawn 15,000 lines. So there will be 15,000 spaces in between the lines through which light can pass. That is, E is the width of each and D is the separation between two lines. So we are taking the grating element as E plus D. Now let us write the formula, have a quick recap of the formula and then do the numericals. So according to Bragg's law, we know that D sine theta is equal to n lambda. This is the famous Bragg's law. But in this case, we are taking the width of the grating element as E plus D. So we will modify it and write it as E plus D is into sine theta is equal to n lambda. So what is E plus D here? It is the width of grating element. And theta is the angle through which the light bends around the corners of obstacle. Angle of diffraction I can write. Theta is the angle of diffraction. And n here represents the order, whether we are talking about the second order or the first order or the third order. N represents the order. And lambda E is the wavelength of light. We are using a monochromatic source. So lambda here represents the wavelength of the light that we are using. So this is clear. So now in some cases, with the help of this grating experiment, you may be asked to find lambda. So lambda will be equal to E plus D into sine theta upon n. Simply we are modifying this formula, rearranging the terms and writing E plus D into sine theta by n. Or in some cases where theta is equal to 90, if it is incident normally, so sine theta, sine 90 is equal to 1. So if theta is equal to 90 degree for normal incidence, we may simply write lambda is equal to E plus D upon n. Now, one more thing what we need to understand here is, in all numericals, the width of the element may not be given. We need to calculate the width of the element. They may give us capital N. Capital N here represents the number of lines per unit centimeters or per inch. So capital N gives the number of lines. So once you know the number of lines, how do you calculate E plus D? So now let us see. There are n number of lines drawn in 1 centimeter. So what will be the width of one line? N lines are drawn in 1 centimeter. So what will be the width of one line means it will be 1 by n. And the width of one line is denoted by E plus D here. So what we understand here is E plus D is equal to 1 by n. I can also modify this formula and write lambda is equal to 1 upon small n into capital N. Now, if you have to calculate the order n, what is the order that is seen means small n will be equal to 1 upon capital N into lambda. So, it's a very simple formula, but how we are going to understand the concept and apply it in different cases. Okay, and here we have taken it is in 1 centimeter. Suppose there are n number of lines in 1 inch. So we always do the numericals in SI system or the CGS system. So we cannot use inches here. So we'll have to definitely convert it into centimeter. So 1 inch is approximately 2.54 centimeter. So we have n lines in 2.54 centimeter. So what will be the width of one line? So that will be 2.54 upon n. This gives the width of each line. So if it is in centimeters, we write directly 1 by n. If it is in inches, we do the conversion. 2.54 by n gives us E plus D. So with this understanding, we will now go to do the numericals. Let us see the first one. A plain transmission grating having 4,250 lines per centimeter is illuminated with sodium light normally. Normally means normal incidence. In second order spectrum, the spectral lines are deviated by 30 degrees. What is the wavelength of the spectral line? So first we will write the data. What is the data given and what we have to find, identify. Here it is given capital N always represents the number of lines. So 4250 lines per centimeter. And here we are talking about second order. So N is equal to 2. We have seen the number of lines per centimeter. We have considered the order and the deviation by 30. Angle of diffraction here is 30. You have to find wavelength lambda. So what is the formula we are going to use? E plus D into sine theta is equal to n lambda. And E plus D is not given, but we know the formula E plus D is equal to 1 by n. So we will modify this as sine theta by capital N is equal to n lambda. So lambda will be equal to sine theta upon small n into capital. So lambda is equal to sine theta, that is 30, by order 30 degree. Order is what? 2 into 425, number of lines. So lambda is equal to, what is the value of sine 30 is 0.5 divided by 2 into 4250. So this gives us 5882 into 10 power minus 10 meter. Lines per centimeter means we would have got 10 power minus 8 centimeter. Now we can convert it into angstrom because generally we express the wavelength in angstrom. So that will be 5882 angstrom. So the wavelength of the spectral line is 5882 angstrom. Now coming to the next one. A source of light having a wavelength of 600 nanometer is incident on a slit of width 1 micrometer. Wavelength is given, width of the slit is given. We have to find the angular separation between the first order minima and maxima on either side. So we have to find the angular separation theta. So what is the data given? We'll write first. Lambda is equal to 600 nanometer. Nm. Nm denotes nanometer. And the width of the slit, that is E plus D, is equal to 1 micrometer. And the order is the first order. We have to calculate theta. So we'll use the formula first. E plus D. Or you can write it as D also here. No need to consider because it's a single slit. Okay, of width 1 micrometer. So you can write it as D also. E plus D into sine theta is equal to n lambda. Or sine theta will be equal to n lambda upon E plus D. So what is sine theta equal to? N is 1. Lambda is given in nanometer. So we need to convert it into meter. 600 into 10 power minus 9 meter. 1 nanometer is 10 power minus 9 meter. And then the width is given in micrometer. So we need to convert this also. 1 micrometer is 1 into 10 power minus 6 meter. So let us write it here. 1 micrometer is 10 power minus 6 meter. So you need to know the conversions. Before substituting, you should make sure that all the given quantities are in the same system of units with the same measure. So sine theta is equal to 1 into 600 into 10 power minus 9 divided by 1 into 10 power minus. So when you take it up, you have sine theta is equal to 10 power 6, 10 power minus 9. So 600 into 10 power minus 3. Or we can simply write it as sine theta is equal to 0.6. Or theta will be equal to sine inverse 0.6. That is 36 degrees 52 minutes. You can write it in decimals also, or otherwise you can convert it into minutes. So what is the angle that we are getting? The angular separation is 36 degree 52 minutes. Now the third one. A plane grating having 10520 lines per centimeter. It is illuminated with light of wavelength 5 into 10 power minus 5 centimeter at normal incidence. So how many orders are available or visible in the grating spectrum? So we'll write the data first. Capital N is equal to 10520 lines per centimeter. And the wavelength is 5 into 10 power minus 5 centimeter. And normal incidence means we'll take theta is equal to 90. We have to find N. So the formula we are going to use is E plus D into sine theta is equal to N lambda. And here the width of the slit is not given. We are given the number of lines per centimeter. So we will modify this and write it as sine theta upon capital N is equal to n lambda, because we have already seen how 1 by E plus D is equal to N, or E plus D is equal to 1 upon N. So sine theta by N is equal to n lambda. We have to calculate the order. So N is equal to sine theta upon capital N into lambda. So this is the formula we will use now. N is equal to sine 90 upon capital N is 10520 into lambda is 5 into 10 power minus 5. So sine 90 is 1. I'll take 10 power 5 to the numerator, so it will be 10 power 5 divided by 10520 into 5. So we get the value of n to be 1.901, which is approximately equal to 2. So how many orders are visible means approximately 2 orders are visible in the grating spectrum. Now the fourth one. A grating has 6,000 lines per centimeter. Find the angular separation between two lines of wavelengths 500 nanometer and 510 nanometer in the third order. So the number of lines are given, wavelengths are given, third order. We have to find the angular separation. Write the data first. Capital N is 6,000 lines per centimeter, and lambda 1 is 500 nanometer, lambda 2 is 510 nanometer, and the order is 3. What we have to calculate is the separation. Theta 1 minus theta 2 is equal to how much, or whichever is greater. So we have theta 2 minus theta 1. We have to calculate. Okay. So the formula we are going to use is the same. E plus D into sine theta is equal to n lambda. I'll write the formula directly here. Sine theta will be equal to n lambda upon E plus D. And because E plus D is not given, capital N is given, I can directly write it as small n into capital N into lambda. So theta will be equal to sine inverse small n into capital N into lambda. Okay. Now let us calculate first theta 1 and then theta 2 and then find the separation. So what will theta 1 be equal to? Sine inverse. The order will not change. The number of lines per inch will not change, but the wavelength will vary. So I'll write lambda 1. This is equal to sine inverse. Here, if we see the units, this is 6,000 lines per centimeter and this is in nanometer. So I'll convert both into meters. So 6,000 lines per centimeter means 6,000 into 10 power 2 lines per meter. So 1 centimeter is 10 power minus 2 meter. So if it goes to the numerator, you have 10 power 2 in the numerator. So 6,000 into 10 power 2 lines per meter. And 500 nanometer is 500 into 10 power minus 9 meter. This is 510 into 10 power minus 9 meter. So let us substitute here. Sine inverse small n is third order, so 3 into 500 into 10 power minus 9 into 6,000 into 10 power. So this is equal to 64 degree 9 minutes. You can use your calculator directly to find the value. Then what is theta 2? Sine inverse small n into capital N into lambda. So that is sine inverse. Small n is 3, capital N is 6000 into 10 power 2 into lambda 2 is 510 nanometer. 510 into 10 power minus 9. So this gives us 66 degree 38 minutes. So when we have to calculate the angular separation, so we have to do theta 2 minus theta 1. So that will be 66 degree 38 minutes minus 64 degree 9 minutes. So that will be 2 degree 29 minutes is the answer. This is the angular separation between the two lines, spectral lines. Next, find the highest order that can be seen with grating having 15,000 lines per inch and the wavelength of light used is 600 nanometer. So what we are going to do here is convert these inches into centimeter. So write the data. Capital N is equal to 15,000 lines per inch, or we write it as 15,000 lines in 2.54 centimeter. Then wavelength lambda is 600 nanometer. So this will be 600 into 10 power minus 9 meter. So if you find this, this will be 5906 lines per centimeter, or I can write it as 5906 into 10 power 2 lines per meter, because if you convert this into meter, this also has to be in meter. Now we have to find the highest order, that means n maximum. So the same formula we are going to use, E plus D into sine theta is equal to n lambda, or sine theta will be equal to small n into capital N into lambda. So for n maxima, we have theta will be equal to 90. So sine 90 upon capital N into lambda. So this will be 1 upon n lambda. So you see how the equation is getting modified because we are finding maxima. So it will be normal incidence. So sine 90 upon capital N into lambda. So 1 upon what is capital N, we got 5906 into 10 power 2 into lambda 600 into 10 power minus 1. So what we get is approximately 2. So n maxima is equal to the number of lines. The order that we can see is maximum is second order. Now coming to the sixth one. A monochromatic light of wavelength 2.5 into 10 power minus 7 meter strikes a grating containing 10,000 slits per centimeter. The number of lines here is 10,000 per centimeter. And determine the angular positions of the second order bright line. We have to find the angular position of second order. So write the data. First is wavelength given. Lambda is equal to 2.5 into 10 power minus 7 meter. Number of lines on the grating is 10,000 per centimeter. order given is 2. We have to find theta. Because this is in meter, we'll convert this also into meter. So this will be 10,000 into 10 power 2 per meter, or we can simply write it as 10 power 6 per meter. 1, 2, 3, 4 and 2. So 10 power 6 per meter. So write the formula now. E plus D into sine theta is equal to n lambda, or sine theta is equal to n lambda upon E plus D. 1 upon E plus D is capital N, so small n into capital N into lambda. So theta will be equal to sine inverse small n capital N into lambda. So theta is equal to sine inverse small n is to second order, capital N we got 10 power 6 and lambda is 2.5 into 10 power minus 7. So what we are going to get is theta is equal to 2.5 into 5 is sine inverse 0.5. So that will be equal to 30. So the angular position will be 30 degrees. Now, what is the angular separation of two spectral lines of wavelength 550 nanometer and 600 nanometer formed in order m is equal to 3 with 529 line per mm grating. This is actually a similar numerical to what we have done before. So maybe the order changes, and here the number of lines given are per mm. We need only to understand to do the conversion. Otherwise the rest of the things remain the same what we have done in the earlier problem for angular separation. So let us write the data. Lambda 1 550 nanometer, lambda 2 600 nanometer, order 3. You can write it as n because we are denoting the order by n, 3. And the number of lines are 529 lines per mm. You have to find theta. So let us first do the conversion, because that is important here, because this is given in nanometer, 10 power minus 9 meter. This is 600 into 10 power minus 9 meter. And this is per millimeter. So we get 529 into 10 power 3 lines per meter. We have to find theta. So write the formula. E plus D into sine theta is equal to n lambda. So sine theta will be equal to n lambda upon E plus D, or 1 upon E plus D is capital N. So small n into capital N into lambda. And theta is equal to sine inverse of small n capital N into lambda. Now first we'll write for theta 1. Theta 1 will be sine inverse 3 into 529 into 10 power 3 into 550 into 10 power minus 9. We'll get theta 1. That is 60.28 degrees. Now let us find theta 2. Sine inverse 3 into 529. Order remains the same. Number of lines on the grating remains the same. Only thing varying is the wavelength. So the wavelength now is 600. So 600 into 10 power minus 9. So this gives us 71.33 degree. If we have to find the angular separation, it is theta 2 minus theta 1. So that will be 71.33 minus 60.28. That is 11.05. So the angular separation between the two lines with the different wavelengths is 11.05 degree. Now, eighth one. A grating with 800 lines per millimeter is illuminated with light of wavelength 550 nanometer. What is the angular separation between two lines formed in the order m is equal to 2? So here we need to understand the problem, and first we'll write the data. Number of lines, capital N is 800 lines per millimeter, or 800 into 10 power 3 lines per meter, or I can write it as 8 into 10 power 5 lines per meter. This is capital N. And wavelength lambda is 550 nanometer. Nanometer also we will convert it into meter. 550 into 10 power minus 9 meter. We have to find angular separation between two lines in the order m is equal to 2. So we have to find theta, and then we have to find 2 theta. Why 2 theta? I'll explain first. So whenever we are talking about a grating, and on the screen, this will be the central maxima. And suppose you have n is equal to 1 here, n is equal to 2 here. And for this we calculate the angle. So this is theta. The same way we have n is equal to 1, n is equal to 2. So here it is n is equal to 1. I'll write precisely minus 1 and minus 2. On the left hand side it is negative, on the right hand side it is positive. So n is equal to 2. First what we are going to find is the angular separation between the central maxima and this is theta for m is equal to minus 2, because we want to find the angular separation between two lines of order m is equal to 2, means m is equal to minus 2 and m is equal to 2. So if this is theta, this is also theta. So the separation will be given by 2 theta. So let us do the numerical. Again use the formula. E plus d into sine theta is equal to n lambda. So sine theta is equal to n lambda upon E plus d, or sine theta is equal to small n into capital N into lambda, and theta is equal to sine inverse of small n capital N lambda. So theta will be equal to sine inverse. Small n we are finding for the second order, 2 into capital N, 8 into 10 power 5 lines per meter we got, into lambda 550 into 10 power minus 9. So this gives us theta is equal to 61.6 degree. But what we have to find here is 2 theta. The separation between two lines of order m is equal to 2. So if this is theta and this is theta, the total angle will be equal to 2 theta. So we write 2 theta will be equal to 2 into 61.6. That will be 123.2. So what is the angular separation between two lines of order m is equal to 2, means it is 123.2 degree. So let us stop here and see you again in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.